Okay, so let's do our fission reaction here, right? So this neutron, this has to be, by the way, a slow neutron. Okay, fast neutrons will actually just go right through that nucleus. This nucleus is unstable. It's just about to fly apart, so it's really not the strongest thing in the world, right? And we basically just kind of lob this neutron gently onto that nucleus, not so fast that it goes right through the nucleus without interacting, but slow enough that it kind of sticks. Okay, so this is a slow neutron, right? And that causes the nucleus to become dyspeptic, and it splits, right? And it also releases some neutrons because this thing has a ton of, look at that. I mean, it's got way more neutrons than protons. That's how many protons? That's not close to half of it, right? Okay, so it's got way more neutrons. So when it makes these things already have too many neutrons, right? So these are going to radioactively decay, and then we're also just going to spew neutrons into space, right? We're venting neutrons when we cause a fission reaction. Okay, that's why I'll always give you these masses, because they're not in our table. All these things are unstable. They're not naturally occurring things. Okay, so our first thing is to figure out how many neutrons. So to do that, let's just write our equation like this. Let's see. We've got, all right, so it's written properly for us here, right? So 235 plus 1, there's 236 total nucleons, and 92 of those are protons, right? On this side, we've got 56 and 36 is 92, right? And 141 plus 90 is 231. Right, so the question is 231 plus what is 236, right? And the answer is that there's going to be 5 on this right side, 5 neutrons. 510 neutrons, okay? So this reaction itself is going to spew 5 neutrons. And the way I got that was I looked at the total number of nucleons. 235 plus 1 is 236. And here we got 141 plus 90, that's 231. 231 plus, we're going to spew 5 neutrons in this case, right? Okay, so let's look at the left side mass of this. We've got this guy, so 235.043932 plus a neutron, and you'll be able to look this up in your data packet, 1.008665, and then that turns into barium 141, and I'll give that mass to you. Plus this guy is 89.919524, and then 5 neutrons, so 1.008665. And that's the most common mistake people make, is you just get the number of neutrons wrong. All right, so let's look at the left side mass of this. So 235.043 932 plus 1.008665, and this is 236.052597, and we're going to compare that to the right side mass of 140.914406 plus 89.919524 plus 5 neutrons, 5 times 1.008665. And again, this is in your data packet, the mass of the neutron. It's not in that table of isotopic masses because it's not an isotope. All right, on the right side, we've got 235 point, holy mass defect, Batman, 7877255. Okay, and these things release kind of a lot of energy, right? So I'm going to find the change in mass, that guy minus this guy. Wow, that's a lot of mass. Our change in mass is 0.175342, and it's negative. So where did all that mass go? Whenever you lose mass like that, right, you should always ask yourself, where does it go? And the answer is that it turns into energy that's released. So So multiply by 931.5. And that is 163.3 MeV, right? Okay. This is released. Okay. So on this side of the equation, you'd have to say plus 163.3 MeV of energy, right? And if you added that up, right, if you go this and this, right, that would add up to this and this and this and this much energy, right? Let me just impress upon you that although this seems like not very much energy, this is a tremendous amount of energy. So if we had some like trinitrotoluene or whatever, nitroglycerin or some highly explosive thing, you would have the energy released would be on the order of tens of electron volts. Okay, this is 163.3 million electron volts. So as soon as they discovered that there were nuclear reactions that were easy to do, just feed this guy a neutron, right? As soon as they discovered that there were these reactions that would release this much energy, they knew that this was a dangerous thing. All you have to do is purify this, which is no easy thing to do, right? This is what we're trying to prevent Iran from doing right now, is getting enough of this, right? All you have to do is get this and then figure out how to trigger the reaction. That's also not super easy, right? You would have a tremendously powerful weapon. But anyway, yeah, there we go. All right.